Hello everyone, my name is Yueting Chen. I'm a PhD candidate at York University. Today I'm going to present our paper, Evaluating Temporal Queries over Video Feeds. This paper is a joint work between York University, University of Toronto, and Yale University. First, I'd like to talk about the background. Nowadays, videos can be easily filmed and produced. How to efficiently store, analyze, and search videos has also become a very important topic. In the computer vision community, many different deep learning models have been proposed to address diverse objectives, such as object detection and object tracking, etc. New applications such as facial detection and event detection have also been applied in real-world scenarios. One of the problems is, how can we evaluate queries over video data? There have been works recently to evaluate queries with DNA models. The idea of this approach is basically to process both videos and queries into the same embedding space and then perform query evaluation or video search inside the embedding space. This kind of approach has some limitations, as listed here. First, it requires end-to-end training for the DNA models. In order to train such models, we must have some kind of annotated datasets. The amount and type of videos in such annotated datasets are pretty limited, and this also limits the scalability of the models and queries. To overcome this issue, we would like to decouple the query evaluation and DNA model inference. Specifically, we only apply DNA models to extract structured data from videos. The query semantics and evaluations are based on the extracted data only. This assumes that the underlying DNA models have solid accuracy and the output error does not have a significant influence on the query semantics. This decoupling brings a few advantages. For example, DNA models are independent of the query evaluation. That is, we can simply take standard implementations of CV algorithms or models and plug them into the system. This also means that for new DNA models or CV algorithms, they can be applied as long as they produce the same results. The structured data extracted from videos can be seen as an intermediate representation of videos, which allows us to enable query sharing and optimizations between queries. Also, we can use declarative queries to express more complex and strict semantics, for example, window semantics. Let's take a simple example. This example shows how we can extract data from videos. For a given video, we first extract the sequence of images from the video, and we apply the object detection algorithm on the images. In this case, we obtain the objects and their coordinates in each frame. Then the detection result will be sent to the object tracking algorithm to obtain a unique ID for each object. In this way, we have turned the video into a relation, where the relation contains 3 columns. FID is the ID of the frame, and ID is the ID of the object, and the class is the class label of the object. In this example, this annotation result is produced by 2 algorithms, object detection and object tracking. Of course, we can use any algorithms as long as they produce the same output schema. The whole process can also involve humans to further improve accuracy. With the relation being produced, many types of queries could be of interest. In this paper, we start with a simple query addressing a counting problem. For example, suppose we are having a monitoring application where we only care about video clips where at least one car and one person appear jointly for at least 3 frames within a window of 4 frames. To express this, we can adopt a SQL syntax and write a declarative query with sliding window semantics like this. In the SQL statement, the co-eval is a user-defined function, which accepts 2 parameters, the query condition, which is written in conjunctive normal form, and a duration parameter, which specifies how many frames at least should the object set appear. Now, for this query, what should be the expected results? From a user's perspective, we would like to be presented with video clips and highlighted objects that satisfy the given query. If we enumerate all possible object set combinations, we could end up with an exponential number of combinations and overwhelm users. For example, given these two frames, where the first frame contains of 4 objects and the second one contains 3, we could generate many unique object sets, but not all of them are necessary. One intuitive solution is to find the object sets that cover most of the objects for different combinations of frames. To this end, we introduce the concept of maximum co-occurrence object set, MCOS. For a given set of frames, an MCOS can be simply generated by intersecting the object sets obtained from each frame. Instead of evaluating queries on all possible object sets, we only evaluate them on MCOS to reduce the number of results. In the previous example, if we only focus on MCOS, we only have to keep 2 unique object sets, because other object sets are already covered by these 2. To keep all possible MCOS, we use stat to store both the object set and the corresponding frame set in the current window. In this paper, we focus on this query and propose a 2-stage approach. It consists of 2 modules, state maintenance and query evaluation. The state maintenance module basically maintains all possible states efficiently and selects a sufficient subset for evaluation. The main optimization in this step is state pruning. Based on the states proposed by the state maintenance, query evaluation then evaluates queries on those states and produce the final results to users. How to share evaluations between queries is the important topic in this part. We first take a look at the state maintenance. The objective of this module is to maintain sufficient states for query evaluation. To reduce the number of states sent to evaluation, we would like to perform some basic filtering before evaluating query conditions. For example, since we only evaluate queries on MCOS, we can send only states that contain a valid MCOS to evaluation. Similarly, we can also push down the duration parameter and evaluate states that satisfy the duration parameter only. To summarize, we only emit valid and satisfied states to query evaluation. Let's consider a simple example first. Suppose we are given a video consists of 5 frames. In this picture, we use the alphabet to represent different objects. The class label of each object is represented by the icon. Assume we are trying to evaluate queries within a window size of 4 frames, and the duration parameter is 3 frames in this case. Now let's consider how to generate and maintain states. Since we only evaluate queries based on MCOS, the idea is we only need to generate MCOS. We can try to intersect object sets between frames and produce new states if needed. This can be done in a sliding window fashion and is summarized into the following rules. The idea is, for each new arriving frame, we compute the object set intersection between the new frame and existing states and create or update states accordingly. We show in the following example. Initially, we generate 1 state with the object set 01 and frame 0. When frame 1 arrives, we compute the object set intersection between 01 and 02. And the result set remains 01, so we append the frame ID 1 to state with 01. The current states are 01 with 0 and 1 frames, and 02 with frame 1. Now let's continue to the next step, where a new frame with object set 03 arrives. In this case, 2 states are created, state with 03, which has the new object set, and state with 04, which maintains the object set intersection result between 02 and 03. The existing states with object set 01 is updated. We add the new frame 2 to its frame set. Similarly, we update the states at step 4. while frame number 3 is being processed. So far, we don't have any expired frames in the window, so all states maintained contain an mcos. We don't have any invalid states. Currently, there are already 4 frames in the window, which is the same as the window size. Suppose we start the window 1 frame further. New states are created and existing states are updated, similar to the previous steps. Now, how can we remove states related to the expired frames? A simple solution is we remove the frame 0 from all frame sets and print states where frame set is empty. Following the idea, states currently maintained are shown in this figure. We can see that the state with object set 01 is not being pruned, because this object set still appears in other frames. But in this case, object set 01 is not an mcos, since it shares the same frame set as 04. To reduce the number of states maintained, the state with 01 should be pruned as early as possible. Now the question is, how can we prune such states? A straightforward way is to check whether the other states share the same frame sets as 01. Apparently, such a procedure could be very costly. So the question is, can we keep some additional information with the state, such that we can easily tell whether to prune a state? Let's revisit the object sets generated by frames. As we can see here, for each frame, there will be a state that shares the same object set. Other states are generated by intersecting object sets between 2 or more frames. We use principal states to denote the states that share the same object set at some frames. Thus, all states are generated by principal states directly or indirectly. Based on the principal states, we propose a marked frame set approach. The idea is to mark important frames that generate the new state. By doing so, we can print states once no frames are marked in its frame set. We are going to use the same example to demonstrate this. Initially, we only have state 01, so we mark the frame 0 in 01 in the state. When frame 1 arrives, we create a new state 02 with frame 1 marked. Since the state 01 already exists, and we only append the new frame to its frame set without marking it. Similarly, we update states for frame 2. For frame 3, 2 new states 05 and 06 are created. Note that up to the current frame, the marked frame sets with 01 haven't been updated, because no other states can generate this object set directly. When frame 4 arrives, we remove frame 0 from all states. In this case, the state with 01 has no marked frame, and thus can be pruned directly. The above procedure can be summarized into the following rules. Eventually, if a state contains no marked frame, then the state could be pruned directly. However, for each newly arriving frame, we still need to iterate through all states. So the new question is, how can we reduce the number of states being visited? As we can observe from the previous examples, all states are generated starting from principal states. If we want to keep the relationships between states in the graphs, then we can apply an early stopping strategy during state traversal. Specifically, we use edges to represent how states are generated. If the object set intersection between a state and the new arriving frame is empty, then there is no need to visit the adjacent states. However, if we construct the graph directly, we may end up with a graph with many edges, as shown in this example. Such many edges could lead to high maintenance cost. So we aim to reduce the number of edges in the graph. The purpose of introducing graph is to reduce the number of stats visited for each new arriving frame. This can be satisfied as long as each stat can be reached from principal stats. Also, since all stats are generated from principal stats, thus we should always visit principal stats. Based on this, we propose to use sparse stat graph. In this graph, we remove all incoming edges for principal stats, and we keep only one incoming edge for other stats. This figure shows an example of converting the previous graph to a sparse stat graph. Now, new question is, how can we build and maintain such SSD? To answer this question, we first take a look at the life cycle of the stat. As can be described here, a stat is created, updated, and removed. In each case, we perform corresponding actions listed here. For example, during stat creation, we can simply create a new incoming edge to the new stat. For the promote and remove cases, we both need to delete the incoming edge of the stat S. Due to the time limit, we will omit the technical details here. To summarize, in stat maintenance, we start with a baseline and further optimize stat pruning using marked frame stat. To further reduce the cost of stat traversal, we use another approach, SSG, to structure stats with minimum overhead. Next, we briefly discuss the query evaluation. With the stats provided in stat maintenance, we can simply aggregate the objects according to their class labels. Then the query evaluation problem becomes a key-value CNF expression evaluation problem with inequality predicates. To enable query sharing, the idea is to index query conditions from a batch of queries. Based on the key-value pairs generated from stats, the queries can be efficiently answered. During indexing procedure, we utilize an indexing technique for Boolean expressions. For each query, we construct an inverted list table consisting of posting lists. The key of the index is the query conditions, including the query label and the query value. The posting list is a list of triplets, where each triplet contains the query ID, the condition operator, and the disjunction ID. We extend this approach to queries with inequality predicates. As for the experiments, we select YOLO and deep sort as the detection and tracking algorithm, and we select videos from different datasets. For the stat maintenance, both MFS and SSG perform significantly better than the baseline, around 3 times faster, and SSG performs slightly better than MFS in some cases. For the query evaluation, we implemented 2 other versions with optimization enabled. The SSG approach with optimization can provide speedups to more than 100 times compared with baseline. In general, the SSG performs better than MFS with query evaluation and optimizations. For more experiment figures, please check out our paper. To conclude, we illustrated a new paradigm to extract structured data from videos and evaluate queries over the structured data. We make the first step of evaluating aggregation queries considering the co-occurrence relations between objects with window semantics. We investigated the stat maintenance problem and proposed both MFS and SSG to prune stats early. We integrated and modified the CNF evaluation algorithm to answer queries efficiently by enabling query sharing. As for future works, we plan to investigate more query types and semantics. Other CV algorithms could be integrated also. How to perform such query evaluations in a systematic way is also worth exploring. Thanks for your attention, and I'll take questions from here.